Hello and welcome, everyone. Today we have with us Imran Ahmad, a data scientist, educator, and author focused on algorithms, AI, and cloud computing. He leads machine learning projects for the Canadian government, teaches at Carleton University, and is an authorized instructor for AWS and Google Cloud. He's also the author of 40 Algorithms Every Programmer Should Know, published in 2020, and 50 Algorithms Every Programmer Should Know, published in 2023, both with PACT. His next book, 30 Agents Every AI Engineer Should Know, is expected later this year. Outside of his professional work, Imran enjoys playing chess, long-distance running, and mentoring developers through his Discord community and workshops. A very warm welcome to you, Imran. It's a pleasure to have you with us today.
Yeah, thank you very much. Thanks for inviting me for this discussion.
Wonderful. So let's start by talking about the books you've written so far and the book that's sort of in the works right now. So the first edition of your book, 40 Algorithms Every Programmer Should Know, came out in 2020. And the second, which was published in 2023, expanded to include 50 algorithms. So what changed in the industry or your own perspective that led to this evolution to include 10 more algorithms?
Okay, so first of all, the 40 algorithms every programmer should know. So those were basically a narration of the world around me, the problem that I was trying to solve. And if you look into these books, these are story-driven books. So there's a story, there's a problem that I'm trying to solve throughout the book. There are a bunch of problems that I'm trying to solve for those books. And algorithms are a tool to do that. They are a powerful tool to do that. And 40 algorithms was when I wrote the first book. 2020 was the time, the sad year of COVID, so we were stuck at home. So I thought that it's a good time to recap, to write a book about the problems that I have solved in the last 20 years. So that book was about that. And to answer your question that why there was a need to write the second edition of that book. So from 2020 to 2023, GenAI, attention mechanisms, transformers, autoencoders, so sequential data became more important due to the boom in the GenAI and the ecosystem around that, So if you look into the world around us in 2020, GenAI was one of the things, but it was not the only thing. Now if you look into, if you ask a college student, ask about that, or if you even ask a person working in a government, or not a data scientist, for that person, AI is GenAI, but so because of the popularity of that. And for the general population, they think that AI is ChatGPT or GenAI, and it shows the importance of that. So those 50 algorithms, basically the 10 algorithms that I added, these are all about sequential data, RNNs, basically LSTM, GRUs, and all those things leading to the attention mechanism, leading to the fundamentals of creating an ecosystem that can work in a GenAI world.
Right. So a very relevant update indeed, especially in today's world. So to add to that, I'd also like to ask, you had a Discord community around the book, I believe. So did any feedback that you received within that community influence the updates as well?
Okay, first of all, when you write a book, so you always think about your target audience, that what is your target audience, And now as an author, you always need to go broad, but not too broad, So you have to choose a balance between the depth and the width, So there are two types of book. One are just sort of, wide books that talks about so many topics, but they do not go deep. The second type of the books, what they do is that they focus on one topic, So now coming back to your question, now if you think about 50 algorithms every programmer should know, now to fit 50 algorithms in a book means that I cannot go deeper into most of them. It doesn't mean that I did not do that. I basically chose some of the important algorithms and talked in detail about that. In a way, I chose that which algorithms need the depth of discussion, the depth of the knowledge. So that was based on what I thought is needed. Now, back to your question. So if you look into the audience, most of them like that, but you cannot, of course, some people will like to have other algorithms to be explained in detail. Some people will, and a lot of feedback that I got was that why don't we have a book specifically on the 10 algorithms that you added in the second edition? Because GenAI, transformers, LSTMs, autoencoders, attention mechanisms, LLMs have become so important, and that's why I'm writing another book that will go deeper into those GenAI world. But for the most part of it, people thought that it is something that they can use for a wide variety of scenarios and use cases.
Okay, wonderful. Actually, my next question was going to be about your upcoming book, and I wanted to ask, what are, would you say the new challenges in AI engineering that you are striving to address with this new book, which is going to be 30 agents every AI engineer should know?
So we have lots of hope around AI that it can replace a human, But if you look into the way a person in a company works to solve a problem, that person has a bunch of tools around him or her, And based on the problem, it sort of in our mind we orchestrate that. Okay, first of all, we do tool selection, and okay, I will first do web search, then I will read a book, then I will email, for example, call my friend, or do some research on going to a library in a university. So, and after that, you create a solution. So agent is sort of replacing that human. It has the ability to discover the tools, the world around it, and it should have the wisdom to orchestrate a solution that is custom tailored for the problem we are trying to solve. We are not there as yet, That's why these 30 agents, this is the next step. This is the next gen of this algorithmic world around us.
Okay, so for the better understanding of our viewers, if I asked you to define the term agent in the context of your upcoming book, what would you say it means really?
Agent is an entity that has the wisdom to work independently in an autonomous way, discover the world around it, that which tools are available, select the right tool, and create a workflow that can solve the problem that we want to solve. That is the dream agent, I call, This is what we strive for. But the agents that are, most of them that we are using, that have part of that ability, So this is the dream agent we strive for, that almost mimics the way I work, So if I'm as a data scientist, I'm working in a company. If I'm given a problem, so this is what I do, right? So if an agent has that wisdom to discover the ecosystem, the tools, the world around it, and use that, and it should be aware of the strengths and weakness of this tool, when to use which tool, and to what extent that tool will be useful, and to use a combination of tools, not one tool. It can use basically verb search. It can use something to do calculus. It can use a paper that is only available in our university library. And it can also use large language models. Large language model is not the only tool. It is one of the tools. And so what we are doing is that now large language model is no more the center of universe. It is one of the important tool, perhaps the most important tool, but not the only tool. Wisdom is outside of the LLM in an entity that is called an agent.
Brilliant. So it's like everything everywhere all at once, like, is super AI being. So thank you for that clarification. And now we'll move on to our next segment, which is about algorithms in the real world and system design. But the first thing I'd like to ask you is, how do you see the definition of core algorithms evolving in today's software landscape? And are there any areas you feel will become essential knowledge in the next few years?
Yeah, so when we talk about algorithms, you can see algorithms from two perspectives. Algorithms from the practitioner point of view, and the algorithms from the researcher point of view. So you need to first of all identify that what is your role, you know. So if you're a researcher, then you need to look into partial differential equations, the optimizations of the algorithms, how basically we came up with the optimal solutions, and what is the proof that this is the optimal solution, and things like that, whether it's NP hard and things like that. As a practitioner, you would not like to go to unnecessary details. The analogy that I give is that it's like a car. Do you want to build a car? Do you want to understand that what are the details of the engine, how many pistons were there, or all those things? Or you want to drive the car? So if you want to drive the car, that is more like a practitioner role. You need to know the essentials to maintain the car, but you don't need to go in unnecessary details. So this is where you first of all you need. This book is written for practitioners. This book is for practitioners, but there are aspects of that that will be relevant to researchers. It goes deeper into those algorithms. It provides a deeper understanding for practitioners so that they know that where the solution is coming from. And the idea is that it helps them for selection of the right algorithm. Otherwise, what's there is that if they just like coming back to the analogy of the car, if you know a bit more about how the engine works, then perhaps you can select the right type of car that suits your need. For all algorithms, if you have just the bare minimum under the hood details, it helps you essentially choosing the right algorithm for the right problem that you can solve.
Brilliant. And that's a great segue into my next question, which was from your own work, Imran, can you share an example perhaps where selecting or optimizing an algorithm made a measurable difference to a system's scalability or resilience?
Yeah, so I can talk about many examples here. So first of all, when you use these algorithms, when these algorithms are taught in university or in academic environment, so they are used on smaller data, sample data, because we have limited time, we need to teach to students. And I call it as manicured, pedicured data.
That's wonderful.
But that is not the real data. The problem with this approach is that people take courses, sometimes online courses, and they sometimes take graduate courses. They use those algorithms, but they're not exposed to the actual data that is out there. That is nothing like the one that we used in that academic world. So coming back to your question, that when we start using these algorithms in actual work, so when the data is huge, the data sets that I'm dealing with, sometimes they have 2 million rows, 5 million rows, 10 million rows. So if you're using graph algorithm on that, so you need to make sure that you are using an algorithm that is scalable. I'll give you an example here. So in the first book that I wrote, 40 algorithms every programmer should know, I explain an algorithm that is Apriori. Apriori is a famous algorithm that is used for if you want to if you want to do association analysis, if you want to discover the causal relationship between the features that you have. If you have weather data, it's an unsupervised machine learning algorithm. But when I actually use that, a priori algorithm wants scale. There's a next generation of that is FP growth. So in the 50 algorithm, the second edition of this book, I replaced that with FP growth, because what it does is that it is a more scalable algorithm. It does not the difference is that a priori it generates the rules, thousands of rules, and then it do the filtering. FP growth, it does the filtering at the source and only generate the rules that are needed. It becomes much more scalable. So this is where, as I mentioned, that as you will start using these algorithms at work, you will find that now things that are important is the non-functional requirements. So in the academic world, we focus on functional requirements, that this needs to be done. For example, there's an algorithm that needs to detect fraud. This is the functional requirement. We will write this down. Things get done. We are happy. But when we go to the actual problem, the non-functional requirements of the performance of sometimes the security, sometimes the solution making itself available as a service. That becomes important. And this is where you will pay more attention to the way, not only the way you prepare the data, but also the way you will use algorithms. Sometimes you will have to use that on the cloud. In that case, you will have to look at a way to make it work in a distributed fashion so that divide and conquer works and your solution becomes much more scalable.
Okay, thank you for that, Imran. A quick follow-up to that. So in performance tuning or system scaling, do you often find yourself revisiting core algorithms, or are these optimizations typically more architectural?
Both, so not all algorithms have tuning parameters, but many algorithms depends on the algorithm. So I'll give you an example. If you are using machine learning algorithm, deep learning, for example, then the batch size that you use, the number of epochs that you're using, your learning rate, the optimizer that you have selected, all those hyper parameters, they are super important in determining that whether your solution will scale or not. The other algorithms for which FP growth, I give you an example, there are fewer tuning parameters there. So yes, you can control the lift and the confidence and the support. You can do that, but you have to find more performant, efficient backend where you will run the algorithm. Cloud is a perfect way of doing it. We are living in the era of cloud, and we are fortunate to be living in the era of cloud. It's a catalyst for creating those large scale solutions that were never possible before. And that is why, these algorithms that we create, many of these algorithms would not work in 20, 25 years ago when cloud was not there. So this is where your creation of infrastructure, a better performant infrastructure, because we always strive for creating elastic architectures that can expand and shrink based on the demand of the algorithm, and that keeps the cost down as well.
Okay, and have you ever encountered a situation where choosing the wrong algorithm caused long-term issues?
Yes. So for predictive analytics, when you are trying to predict something, so if you now let's assume that you are trying to approve or refuse the mortgage for a person applies at a bank for mortgage, and you are approving or refusing that application. So you can go by the simplest approach is you can go by just rules, by the intuition. Based on that, you can go by rules. Then based on that, you can create a decision tree so that there is more explainability. Decision trees are explainable. They are white box algorithms. They are usually the first choice in financial sector, government, healthcare, where that explainability is paramount, that is necessary. But sometimes what happens is that decision tree is prone to overfit. Decision tree is also prone to, sometimes if there is a correlation between the features of the data, then decision tree won't perform well. So in that case, you have to move to an advanced algorithm. If you don't want to go to deep learning, then SVM, XGBoost is a good option. That essentially what it does is that it addresses those limitations of a simplistic algorithm like decision tree. So I've gone through that process for using this in the predictive applications, and sometimes so this whole process is iterative. You start using it's a good choice that you start using a simple algorithm, test the results and slowly move towards more complex algorithms instead of choosing a more complex algorithm in the first iteration. And sometimes it's an overkill. You are sort of lifting a paper with a crane or a forklift. That is not required. You can just so yeah.
Yeah. So I think my next question was actually, so that was a good piece of insight and advice based on your personal experience, actually. So my next question was actually, how do you advise engineers to integrate algorithmic thinking into architecture level decisions, especially when working with distributed systems or cloud platforms?
So first thing is that this is the era of machine learning. So let's start with machine learning. So machine learning algorithms, if you look into that, they have very different requirements in training testing, and in production. The architecture requirements, the hardware requirements are very different. When when you're training the model, you need huge, you need lots of data in order to make conclusive evidence of the causal relationship between the features and the label. Otherwise, it won't be satisfactory training model. So for that, you need data. And for that, in order to process the data, you need processing power. You need GPU. It's expensive. It's time consuming. So in that case, the cloud computing provides you the elastic architecture. You can even have 2000 nodes for 2 hours or 10 hours, and then we are done. The cost is manageable, but and the time is manageable as well, because of the elasticity, you provided those 2000 nodes for those 8 hours. You paid $100 it's still manageable, but not so. But once you have trained and tested the model itself is a very small file. Sometimes you can look at that and just laugh that this is sometimes I call it as the tail of an elephant. Elephant is so huge, but if you see an elephant, the tail is really teeny tiny. So the trained model is in many cases the tail of that elephant. It's a very small file, and you can even deploy that on your iPhone, or your Android phone to use it. So it means that the hardware requirements in the different phases of that algorithmic process are different. So if you want to control the cost and you want to make it performant, then choose systems that are elastic. And the cloud computing is our best shot at that. Doesn't matter you use AWS, Google, or Azure, doesn't matter which one do you use, but use a cloud.
Okay, wonderful. And I'm really liking all the metaphors you've been using. That is also present in the books that you've written. And for our viewers, if you want to learn, really complex subjects in an engaging and story-driven way, do check out Imran's book. So a follow-up from, what we were just discussing right now. Are there any patterns or heuristics you use currently to identify when algorithm choice should drive architectural decisions?
Yes, so it depends on the complexity. So if you are trying to solve something simple, algorithms can be used in any scenario. They're very simple, medium, complex. So over design is a problem. Sometimes sometimes we overthink. So if a simple design can solve the problem, then use a simple algorithm and go for it. But if you need, so first you need to determine that do you justify bringing additional complexity in the workflow, in the architecture, because you want to use this algorithm? Do you justify using it? And what is the cost benefit? So you look at the returns in three dimensions: cost, performance, and time. And what it means is that whatever you're doing, at the end of the day, it will increase the cost increase the cost in terms of increased hardware requirements, the time that you spend, the cost will increase. So it means that do you justify that with the time and the accuracy? So whatever you're doing, is it more accurate? Is it more cost effective? And at the end of the day, you can justify the cost it's more cost effective. And is it more time efficient as well? Three things: time, accuracy, and cost. So you have to look at that metrics to see that which algorithm essentially optimize that, right? So that would be a good way of selecting the right algorithm for a given problem.
Okay, brilliant. Thanks for that. It was very clear and helpful. Now let's move on to our next segment, which is about the intersection between classical algorithms and AI and modern workflows. So the first question I have for you: classical algorithms like graph search or dynamic programming often underpin modern AI systems. Could you share an example where these so-called old techniques support cutting-edge AI today?
Yeah, so what I think is that they complement each other. It's not that they are rivals. In some cases, yes, they can solve, there is an overlap. But in many cases, for example, search algorithms, now so when you are preparing the data, when you are selecting your data sets for AI, so you can use search algorithms to, if you have a data lake, for example, let's say that you are working in an organization and you have structured data, you have unstructured data in a data lake, and now you want to train a model for let's say that you are doing fraud detection, and for that you want to train the model. Now, how you are going to find that which relevant features and which relevant data set is there in the huge repository that is a data lake? Search algorithms can help you identify those data sets and help you prepare for it. So in that case, you can see that they are not rivals. You are using those classical algorithms to complement, to prepare the data for your AI, because for AI is all data driven. So classical algorithms that are there, they are mostly applied on the data for searching data, for doing link analysis, for example, in many cases, establishing the causal relationship, cause and effect relationship between the features, trying to find the quality of the data, trying to see that whether we can mine information from that, classical NLP algorithms, all of that can complement our AI. It's not that I don't see that as rivals. So those knowledge of that algorithm will, in fact, you can see that this is a different muscle. So if you go to gym, so you want to develop your biceps, but you also need to pay attention to other muscles as well. So perhaps AI is the most important muscle, but it doesn't mean that other muscles are not important. For a strong body, you need basically to work on all the muscles to get performant body, and in this case, a performant, efficient architecture.
Brilliant. So could you give us an example, perhaps, of a specific hybrid approach where classical algorithms support AI systems in production?
Yes, I can provide that actual example. So let's say that one of the classical algorithms I will go back to is Apriori algorithm. The next version is FV growth. Now, Apriori algorithm or FV growth, they are used for association analysis. Association analysis, in my point of view, it is one of the most powerful technique, most powerful algorithm. And this is also one of the most underutilized algorithm as well. Now, what it does is that you do not provide a label. What you do is that, let's say you have 20 features, you just feed that features to that algorithm. It will try to create relationships between them. So let me give you an example here. Let's think about uh, just a couple of hours ago, I went to a corner shop to buy milk. So let's go with that example. Let's say that I have the data for the last 1 month from that corner shop, and I feed that to Apriori. The selling data, that all the items and that were there, that were bought. So the data that we are collecting is that when someone pays for the shopping, so we collect the data that this person has bought these items. So this is all data that we have. So the transactions. So let's assume that in the last 30 days there are 10,000 transactions. So there will be 10,000 rows, and each row will represent the items that have been bought in one sale. Right? We feed that to FV growth or Apriori algorithm. It will tell us that, first of all, what is the relationship? If someone is buying milk, that person is also buying cheese. If someone is buying, for example, say shaving razor, and that person is also buying shaving gel. So it will establish those causal relationship. Now, that is a classical algorithm, right? Based on that, what we can do is that we are trying to now use AI. It will give us insights that what are the relationship between these items. And label is, as I mentioned before, that in manicure pedicure data that we use in academic settings, the label is always clear that this feature is a label. In actual data, the label is not always clear. It's not clear cut that this feature is a label. So sometimes we have to use a derived feature that is basically a derivation of 2 or 3 features to create a label that we'll be using. Now, coming back to this one, a priori is a powerful technique to understand the relationships between the data, to identify that which one is the potential label, and in some cases it can give you insights that how you can process those data to come up with the right label. So in this case you will see a priori it's an old algorithm. You see the history 30-40 years ago it was popular. Now AI is modern, and now those classical algorithms, they complement what we are doing in AI. That's why the knowledge of all the algorithms make you better programmer, better AI engineer.
Brilliant. And I think we're going to talk about that a bit later. But before that, optimization is key in both classical algorithms and AI models. What are some common mistakes that you've seen engineers make when trying to optimize systems combining, both these worlds?
Okay, so first of all, optimization is very important. So how important it is, let's talk about it. So when you do math is cruel in many ways. How? That if you are not careful, your problem won't converge in sometimes not in hours, not in days. If you are not careful, if you somehow put an unoptimized solution, and there's a some way there is an exponential that shows up at the wrong place, so it may take years, it may take centuries for problem to converge. So it's not that someone can say, okay, I can, I'm not in a hurry, I can wait for a couple of hours. So I don't want to spend time on optimization. Not a big deal. I can work on my thesis, and I will let my desktop converge the problem. I can wait. So first thing is that in algorithms, very soon things can become out of hand. So the sun will die. It will run out of energy, and the a million of years down the road, and the algorithm will still want converge. So this is one thing. So it's super important to look at what solution you are creating, because it affects your time, it affects your cost, and it affects the feasibility of the solution. Now, coming back to your question, that especially for machine learning, that is why this optimization is not a luxury, it's a necessity. You have to do that. Now, optimization can be done at more than one levels. First of all, use of GPU. If you're using a deep learning algorithm, use of GPU can speed up your performance by 1,000 times. If I've mentioned that in my book, one of the last chapters, second last chapter, talks about it, that why it speeds up. It's not that, so you need to have GPU if you are looking for deep learning, complex, so you cannot live without that. So this is again optimization on the hardware level. Now let's take a step back and let's see that what we can do in the hyperparameter tuning and how we can use the classical algorithm for that. Now, if you look into the hyperparameter tuning, now these days this is where we used to spend lots of time in finding the right mix of hyperparameters. Now, what Google has done is that they have a tool that is called Wazir. Now, Wazir is a tool that can help you find the right mix of hyperparameter. If you have a background from, if you have looked into the history of Ottoman Empire or Mughal Empire or the empires around the world, it's not that we support them or we don't support them, but in those empires, there was a person that was called Wazir. Wazir was the next to the Sultan. And the Wazir, what it will do is that it will support the governance to function it better. So this is the name that is chosen by Google. It's called Wazir. And that Wazir, the kingdom is the model that is being trained. And the Wazir is assisting that training process through selecting the right mix of hyperparameters. So use Wazir. Don't basically use hit and try to do that. Now, Wazir is based on classical algorithm. It is based on heuristics. It is not. It will. There are two types of algorithms that algorithms that give you a solution that is proven to be optimal. Heuristics means that there is no. It is a good enough solution, but it will take too much time to convert. So, we can live with a good enough solution. So there is no proof that this is the best solution, but we think that it is good enough. That is based on heuristics. So Wazir is based on classical heuristic-based algorithm. And now you can see that Google has suggested us to use that for hyperparameter tuning. And that is super important, for example, for complex algorithm training, like training a deep learning model.
Okay, so Wazir, in addition to Wazir, are there any other tools or techniques you recommend for engineers to use for perhaps profiling and diagnosing algorithmic bottlenecks in AI workflows?
Yes, so you can do that at multiple levels. So first of all, what is AI? AI is about formulating the signal that is coming from the patterns embedded in the data. You are formulating that signal. What that mean? That if there is a signal, if you have data that shows that this is the evidence of fraud. So if you have, say, 100,000 data points, and some of them show the evidence of the fraud, some of them do not show the evidence of the fraud. And AI is about, first of all, formulating the differentiator that can differentiate between what is fraud and what is not fraud. That formulation is AI. That is about training the model, understanding, detecting the signal, and formulating that. So before you use AI, you and AI is a time consuming process. I have explained the crisp DM life cycle, the life cycle of an AI project. You do, you understand the data, then you do data prep, then what you do is that you use model training, then you testing, you deploy. So the first phase, when you are doing data understanding, this is where you can use the classical algorithms to understand that whether we should go ahead. So let's assume that our data has randomness. It means that there is no clear differentiator that what was the evidence of fraud. There is so much noise there. If there's noise, there is a problem with data quality right there. And in that case, you should not go ahead with machine learning. This is no matter if you even bring a person with the Nobel Prize, they won't do much there, because there is noise in the data. It means that before you go towards the crisp DM life cycle, you go ahead with the next phase of AI. First, you need to understand the data. In that case, all the algorithms that I talked about, for example, that the searching algorithms, the dynamic programming, or the classical algorithms that can help you. First, it will depend on different use cases as well. For IoT devices, that may be graph databases. You can choose a combination of that. For people data, like the data that you will find in government, financial, healthcare, you can use. Again, you need to confirm that there's signal in the data before you go ahead.
Brilliant. Thank you for that, Imran. Now we'll move on to our final section of the interview, where I want to dig a little bit into your teaching and mentoring experience to get some advice for professionals in the field. So the first question I have for you is, many developers learn algorithms for interviews, but struggle to apply them meaningfully in real systems. How can learning approaches evolve to make algorithmic knowledge stick?
So if you learn an algorithm for the interview, so it's a good start. It's not that, so at least you have made an effort, you have and now when you learn the algorithm for the interview, you are not you are not using it to solve an actual problem. So what you will do here is that you will prepare yourself for the algorithm for the interview. You will try to guess that what type of questions will be asked, what type of now interview. When someone takes an interview, that person has limited time. So that person cannot, there is no way that person can go into the details, the problems that you will face when you will actually implement the algorithms, the strength or weakness. So that will be a shallow knowledge, and you are expected to have that shallow knowledge. So in most of them, I won't say, if you are, for example, you're applying for a deep learning job at Google Brain, then of course they will go into in detail. But if you are applying for as a programmer, then I don't expect that they expect you to know the hyperparameter tuning that you will use in FP growth. I don't expect that. In that case, the general knowledge of FP growth is good. But now this is again a good start. But if you want to actually use algorithm as a tool, then the only way you can do that is to start using to solve an actual problem that will expose you to the issues that will point you, you will be amazed that to use that algorithm, you may require to have knowledge of other algorithms to prepare the data, to optimize your solution, to deploy that in a scalable way, to create a backend architecture. So there is an ecosystem, there is a community of algorithms that support each other. That's why I say that both classical and modern algorithm, they complement each other, and the knowledge of that is required.
Fine. So, follow-up question from, what we were discussing just now. Do you have any favorite practical exercises or projects that help solidify algorithmic understanding beyond textbook examples?
Yes. So the projects that I would suggest is, first of all, they should be your use case driven, but I can suggest some. So we call them as verticals. They are horizontals or verticals. So horizontals are the concepts, the methodologies, the algorithms that we discuss in the context of a broad spectrum of things. Then you choose some verticals. Verticals that are my favorite. It depends that government, because I work in government. When you use this algorithm, let me talk about a bit about this. So when you work for government is the legal custodian of data for its citizens all across the globe. It can legally have the data about the citizens, the depth of the data, the criminality data, in some cases the data about health, the data about immigration status, the data about employment. So if you are working for government, and you can create solutions that can change the life of the people. There's a noble aspect to that, if you think about that. So, and the government has so much across the, you talk, these days, any country, on the globe will have data about the citizens, and if used in the right way, it can, for example, identify the vulnerable communities. It can identify the people that need those services. It can make government more efficient. It can make them cost effective. It can uplift people from the poverty. It can actually make large scale improvement in the lives of the people that are tangible. So if you have access to that data, so I would say that there is, so all governments across the globe, most of the governments, now they have public data sets. The biggest of them is data.gov, that is offered by US governments. They are close to 500,000 data sets from all three level of governments. So if you want to choose a project, go to that website, data.gov, choose a data set. If you are concerned about environment issues, if you are concerned about, for example, pollution, if you are concerned about efficiency of the government, if you're concerned about the cancer treatment, so all those data sets are there, as well as traffic data, flight data. You will be amazed how much data. It's a heaven for any data scientist, and people don't know that. Data.gov. So there's a similar data site on a smaller scale by Canadian government. There's a similar data site on a slightly smaller scale by European government. And there's a data site about that is India government also has one of those data sets. India government, if you look into that, they are also making lots of progress in making the government open and accessible to its citizens so that they are accountable. So if you want to use this algorithm, first you need data. As I mentioned, without data, these algorithms, where you will use that? And the data needs to be not the academic data, you need actual data set. And now in 2025, we have luxury to have those data sets through these open government, data sites. Choose the vertical that is relevant to you, download the data set, find an algorithm, and solve a problem. This is the best way you can move forward.
Okay, brilliant. That was really useful information. Thank you for that. Now, moving on to my next question, which is with AI, cloud, and distributed systems evolving rapidly, Where should software architects focus their algorithmic learning today?
So from the software architects, if you're talking about architects, their role is to create a performant and cost effective solution, so their aim should be to help company buy Toyota Corolla, you know, Ferrari at the cost of Toyota Corolla, Ferrari, a car that is as expensive as performant, Ferrari at the cost of Toyota Corolla, So they need to design the systems in a way that are performant and cost effective at the same time. That was not possible 10 years ago, So whenever they're thinking about that, so they always need to be thinking about the word that I used over and over again, elastic architectures that can expand and shrink based on the need of the algorithm. Don't let the server keep running if you're not using an algorithm. Scale that down, so that elasticity is super important because that controls the cost. And it also, now this elasticity can be provided at the data level, at compute level. If you're creating a cluster, that elasticity should be there. Resilience is important, but yes, we can live with restart. That's when you are using these algorithms, if you are not using that in production. So redundancy is important, but pay attention to elasticity, pay attention to elastic architectures, and see that how you can make those choices. Elastic architectures usually are not the first choice of the architects because this is not the simplest choice. So you need to have level 3 of maturity. You need to have more maturity, you need to have deeper understanding of your infrastructure to make them elastic.
Okay. Thank you for that. So, as someone who teaches and mentors, what skills or mindsets do you recommend for engineers aiming to stay adaptable in the next wave of AI and systems development?
So this is about keeping yourself curious. Things are coming, new things are coming each day. Keep yourself informed, keep yourself connected to the people who are working in this domain. If you will not, for example, as they say, if you don't learn AI will replace you. I don't fully agree, but this is partly true. So if you fear using these algorithms will replace you. If you if you if you consider them as a tool, then it will make you more efficient, more performant, more capable, and more useful. So this is the way you should not fear. And one thing is that you should also filter the noise from the signal. There's lots of information available, and most of them is wrong. If you look into, I'll give you an example here. Now, prompt engineering is a topic. The prompt engineering, I teach that in some courses as well. Most of the information that you will find on LinkedIn, on the web pages, the blogs that people are creating, that is just wrong. That does not work. So that is why it is important to find a reliable source, reliable, a person, a company that know that what they are saying, that not only know the things on the surface, that they know what is under the hood, so that you have limited time. If you want to train yourself, you want to learn, you want to basically choose the high quality contents to make sure that you are making the best use of the limited time that you have.
And Imran, are there any emerging areas in AI or distributed systems where you believe algorithmic thinking will become very, very critical?
Yeah, so the area that is, as we know, this is Gen AI, but let me talk about Gen AI. So for people who know these large language models are essentially, in a way, you can think about that as encoder and decoders, auto encoders, or we have looked into that. But this is a process of encoding, processing the information, and decoding the response. Request comes in, it gets encoded, it gets processed, and the response come back. So as the things stand today, either we can pay more attention to encoding process, we can consume more resources in encoding process, or we can pay more attention to the decoding process. We have limited resources. We cannot. So right now, if you see, most of the solutions are more GPT based than BERT based. There are two architectures, GPT and BERT. BERT, BERT, and GPT. Now GPT is more encoding based, and they are fast. But now we are heading towards solutions that need thinking, that need decoding, that need to understand the problem well before answering. That is why you will see that in GPT, for example, there are tools, there are agents, or in Gemini, you will see that they take time to think. They do not respond straight away. Sometimes they will take 10 minutes or 20 minutes to think and to get the information that is required. Now, those 10 or 20 minutes are our first attempt at that. They will be reduced to 2 minutes. So it means that the responses that we are getting from these automated generative solutions, they will be much more intelligent, but the time will be right now it's about 20 minutes. It will come back to 2 minutes. This is where this is one point. The second thing is that now this Gen AI, if you think about this can also be this request and response that can be applied to robotics. Now robotics, a robot can be trained, for example. For example, I ask a robot, if let's say there is a robot, I'm doing some experiments with that here. So I say that, okay, do this task. Now, is there a possibility that there is an embedded large language model that is, Jettison, that is right here? Now, Jettison is a small, system. You can embed a large language model within Jettison. You can attach to a robot. Now, it means that Gen AI can at least complement the reinforcement learning that we were classically using in the robot. So this is where the research is happening, and this is where the future is.
Okay, that's brilliant, Imran. And that brings us to our final question for this interview. So we'd like to know, looking back at your very long journey across academia, government, and training, what has most shaped your approach to problem solving and teaching?
So the approach is something, creating something that people find useful to solve a problem. So we should be focused on the functional and non-functional requirements, and the criteria of success is to address that. I'll give you an example here. So some of the courses that are taught in university about algorithms, they go in unnecessary mathematical details. So it means that if we are teaching people to how to optimize an algorithm using very complex partial differential equations, nested partial differential equations, and we spend a week, and after that we say, okay, now we can prove that this is an optimal algorithm. Now, yes, this is important, but in the case of the way we can keep people engaged, the way we can keep people, we can communicate that these are useful technology, extremely useful technology, is keeping the problem statement in mind, what we're trying to do. What is important, how is important. So this is all how we are doing it, right? But in the process of zooming into how, do not forget the what part of it, what needs to be done. And how is one way of doing it. The other ways of doing that is, ability to create more than one solutions, compare them, select the right solution, and come up with something that addresses the actual problem is important. And this is what I at least always keep in mind.
Brilliant. Thank you for that, Imran, and for your time and all the valuable insights that you've shared with us. It's been a real pleasure having you with us today. And even I have actually learned a great deal. So thank you for that.
Okay, so you are very welcome, and good luck. And if so, this is my first book, 40
Yes.
Every Programmer Should Know, and this is the second one. And wait for the third one. It's coming in October.
Yes, and so leading on from that, for our viewers, do check out Imran Ahmad's most recently published book, which is 50 Algorithms Every Programmer Should Know, for more deep real-world insights and examples. And we'll provide the link for you in the description under the video. And also keep your eyes peeled for the next one, which is going to be 30 agents every AI engineer should know. See you all next time.